Okay, guys, welcome back to Grade 9 Science in the Optics unit. For those of us that are joining asynchronously, we are just going to go over the plan for the day. We will have a quick discussion of the Ed puzzle and the Gizmo that you just completed, as well as the Ed puzzle that you have for today's course, as well as worksheet 7. So, starting with the Gizmo starts out with some prior knowledge questions that are designed to be a mind activation activity for you guys and get you thinking about what you already know about light rays and the electromagnetic wave properties of light. So question number 1 asks you, draw the path the sun rays will likely take from a magnifying glass to the grass if we know she wants to use the glass to focus the sunlight and start a fire. So we know now, given the tutorial from last class, that a magnifying glass is a convex lens where the rays will converge. So we know the key word here is that she wants to focus the sunlight and start a fire. So she's going to therefore focus the rays by having them converge to a single point. So why is this useful? Why is a convex lens useful for starting fires? Well, the convex lens has the rays converge. So convex, converge, and we know that it's going to converge because, I just realized it's not sharing for some reason. We know that it's going to converge because convex and converge both have the V in the middle of the word, and concave and diverge, the C in concave and the D in diverge are close in the alphabet. So we know we can memorize using that anecdote that convex lenses will converge. So we draw the rays converging to a single point. Why is that useful? Well, given the electromagnetic wave properties of light, we know that these light rays all have energy. And this energy can be used and transferred to heat energy. And in this case, starting the fire on the dry grass here. So that was the activation minds on activity. The Gizmo warm-up just had us explore through the different tools that we can use in the Gizmo and taught us how to identify the lines. So it asks us to begin by turning on the colorized lines in the checkbox and turning off the central line and the line through focal points so that only the parallel line is showing. Parallel meaning the incident ray is parallel to the principal axis. Okay, so that line is showing. It then asks you, the blue dots in front of and behind the lens are the focal points. Move the candle on the left back and forth and up and down. What is always true about the light ray that emerges from the right side of the lens? The answer that you guys should have noticed is that the line emerges from the right side of the lens always passes through the focal point. And that's a rule for convex converging lenses. So a parallel line, a line parallel to the principal axis, will converge to the focal point. So an incident ray parallel to the principal axis, as shown in the image here, will converge to the focal point. The second rule that we explored was the line through a focal point. So if our incident ray goes through the virtual focal point and then makes contact with the lens, where is it going to go? It will converge parallel to the principal axis. So just the opposite of question number 1. Okay, so now that we've identified with the simulator and we know how to work it, it asks us to set up the simulator for a number of experiments we're going to run. It tells us to turn on all 3 lines and move the candle to minus 24 units on the central axis and the focal point to minus 12. So once we've done that, it asks us to observe in its current configuration the distance between the candle and the focal point. So if you look at the total number of units, you'll notice we're at 2F, right? Where F, the focal point, is at 12 units. Our object is at twice the distance from the lens at 2F at 24 units. So what do you notice about the orientation of the candle's image? This is just asking you about the salt of the image. So what do you know about its orientation? Well, it's upside down. What about its size? Well, it should be the same size. When it's at 2F, an object should be the same size inverted behind the lens. It then asks us to make a number of different movements with minus 24 units as our starting point. So at minus 24 units as our starting point for the candle and minus 12 for a focal point, it asks us to move the candle to the left. If we move it to the left, we're moving it away from the focal point, away from the lens. What we should notice happening is that the image moves to the left and the image produced is smaller than the original object. It then asks us to reset. After resetting, it says move the candle to the right. As we move the candle to the right, remember, we're therefore moving the object closer to the focal point and closer to the lens. In doing that, the image displayed should have been bigger and should have moved to the right. It then asks us to move the left focal point to the left. So moving the focal point this time with the candle staying at 24 units. When we do that, the image moves to the right and gets bigger. It then asks us to move the left focal point to the right. Now we've moved the focal point further away from the object. So what should happen? Well, when the object is further from the focal point, the image gets smaller. And that's the trend. The closer the object is to the focal point, the larger it will appear on the other side of the lens. So the analysis asks you to form a relationship statement about the distance between the candle and the focal point. And that relationship statement should have read something similar to, as the distance between the candle and focal point increases, the image gets smaller. So as we move the focal point and the candle away from each other, the image produced gets smaller. The image grows larger as the distance between the candle and focal point decreases. So as the candle and the focal point get closer together, our image produced should be viewed as a bigger image. Okay. It then asks us to explore the difference between if we put the candle in between the focal point and the lens. So now it asks us to switch the location of the candle and the focal point. So the candle we move to minus 12 units, and the focal point we move to minus 24. So a visual representation, I'll see if this works, a visual representation of that would look like this. Oh, it's not going to work. Hold on. See if I can get my pen to work here. Annotate. So a visual representation, we now have our focal point here along our principal axis at minus 24, and then at the halfway point at minus 12, we have our candle, and then at 0, we have our axis of symmetry, and we have our axis of symmetry, and we have our convex lens. So it says when we do this, what happens to the image produced? In this case, what we should see is that the image produced is magnified and located to the left of the candle as a virtual image, which makes sense. If you think about it, the rays that go through the focal point, in this case, those rays need to go from the virtual focal point behind. So it needs to extend. And what you end up seeing is a virtual image. I'm not sure if I can erase this here. There we go, eraser. So the investigation then asks us to return the candle back to its original location at minus 24 and the left focal point to minus 12. Under show specific line segments, it asks us to turn off our apparent lines. That way, when we select concave lens, we'll be asked to analyze the appearance of a virtual image. So it asks you, what do you notice about the 3 lines after they pass through the concave lens? The 3 lines spread apart. So these are called diverging rays. And as such, we call the lens a diverging lens. It then asks us to turn on apparent lines. Is the image of the candle real or virtual? When we turn on apparent lines, we know even more so that it must be a virtual image because we're seeing the extended lines now, and we know that no real light rays are converging or focusing at that point. Those are just the extended apparent light lines that we've added. So we know even more now that this is a virtual image. Question C asks us to move the candle back and forth, and no matter where the candle is placed, what is true about the image? Well, it turns out that the image is always upright, virtual, and smaller than the candle. Question D asks us, what would an observer see if she looked at the candle through the concave lens? The observer would see an upright virtual image that is smaller than the candle itself. So those are kind of the rules now that we can take and apply to concave and convex lenses. And today, we're going to use this summary to help us analyze and produce some ray diagrams for converging convex lenses. The summary question asks us, what are the differences between the images formed by convex and concave lenses? Sample answer, the convex lenses can produce real and virtual images. Okay, so we saw real images produced when the candle's object, or the object, in this case a candle, was located outside of the focal point. Between the focal point and the lens, we noticed that an object between the focal point and the lens would produce a virtual image. So these images may be magnified or shrunk depending on how close they are to the focal point. The closer they are to the focal point, the bigger the image produced. When looking at a concave lens, no matter where the candle or any object is located, a concave lens will always produce a shrunken virtual image. And that's it for the Gizmo. So I'm going to stop sharing my screen on the Gizmo for now and wrap that up. I'm hearing some feedback that it is glitching out or lagging out right now, and I apologize for that. I can't change that at the moment. But when I do post the recording, you will see, hopefully, everything posted just fine without any lagging. So I'm going to now skip over to today's work in the OneNote. And then I'll send you guys off to work on worksheet 7 and the Ed puzzle. So converging lenses. When drawing ray diagrams for lenses, it's very similar marking scheme to that of drawing mirror diagrams. So the marks will be out of 5 for each diagram, typically speaking. So where do the marks come from? Well, you get 2 marks for your communication of the orientation of the image. So the salt, half a mark for each. You get 1 mark for drawing the appropriate rays. There are 3 rays that you need to draw for lenses, just like for mirrors. Then you get 1 mark for properly locating and producing the drawing of an image, and 1 mark for labeling each of the 4 following elements: the virtual and principal focal point, the axis of symmetry, and the principal axis. Labeling all 4 of those with the correct salt orientation, correct rays, and image gets you 5 marks out of 5. Okay, so there are 3 rules that we need to summarize from the Gizmo and today's lesson. The first rule of a converging lens: any incident ray that travels parallel to the principal axis will refract through the focal point. Any incident ray that passes through the virtual focal point will refract parallel to the principal axis. And finally, any incident ray that intersects the axis of symmetry and the principal axis of the mirror will emerge in the same direction. So those are the 3 rules summarized in one image there, and some examples of locations of object and image produced here. So without further ado, I will leave you guys to complete worksheet 7, convex converging lens ray diagrams. There are a lot of examples here for you guys to work through. So when you're done this, you guys should be pros on convex lens diagrams. You also have an Ed puzzle to do for homework. That's what you have for classwork today and homework. Hopefully it's not too much. You guys asked to slow things down a little bit on the experiments and take some time to review, and this is a great opportunity for you to do that with today's work. So I notice I have 2 people with their hands up, so I will take a moment to answer these questions. I'm going to pause the recording now and take any questions that we might have.